welcome back. So it's a great pleasure to welcome back Vakhtang Poutkaradze from the University of Alberta up in Edmonton. He comes here to warm up, although we didn't really oblige him this time. Anyway, so he's back here in Minnesota, and he's going to talk to us on Lie-Poisson neural networks and database computing of Hamiltonian systems.
Yeah. Thank you very much, Peter, and thank you to IMA for inviting me. It's great to be here, and after a long pause, but hopefully the next pause is not going to be that long. So I wanted to talk. This is something I've been doing for the last couple of years, and I started that when I was in sabbatical in Albuquerque, and it's a joint work with Chris Eldred from Computer Science Research Institute, my longtime collaborator, Francois Gelbalma, who just moved to NTU Singapore, and my grad student, Sophia Huraka. And the two papers on this have been published in Neural Networks. I can tell you, because I was in Albuquerque, those of you who like Breaking Bad, everything in this business has to be called, it's a snazzy name, Nets something. And so we invented this name, LPNets, driving Chris's truck from Loyola's cafe, where they filmed a lot of Breaking Bad. So this talk combines art and science, if you call Breaking Bad art. So this is and I apologize if for some folks here, it's a little too trivial, but I wanted to get a background in neural network. And there's a traditional artificial neural networks, just feed forward, nothing fancy. And so what is a neural network? It has these objects we call neurons, but they are actually just nonlinear functions. They have to be nonlinear. And then there you have some inputs. I call them X. And some outputs are called Y. And so the inputs, they're digitized somehow, and they summed with something called weights. And they put into this neuron. And of course, it's not like real neuron, but it's sort of a model of neuron on some levels. And then the output of this function is put in the next level, and then it comes out into Y's. And so, for example, X's are the products you browse on Amazon, and Y's are the shampoo you're going to buy. And so, if you believe that there is a connection between X and Y, and this connection is numerical, then you have to believe that. Then there are some theorems in this neural network that say you can approximate any function that satisfies some conditions. And so what is the training? Well, you want to find that function that maps inputs X to W to output W for every, to output Y for every W. And you consider something called loss function, which is usually, for example, this the mean square. This is the one we will consider, but there are all kinds of other loss functions. And you optimize the weights in such a way that you have this loss function is minimal. And then you say, okay, so that for every input, you have an output. But the problem is that this is called purely data-based computing. And of course, it works sometimes good and sometimes not so good. But it's okay if you try to predict sort of things like shampoo buying, because there's no repercussions. But I worked, some of you know that I worked a few years in a company, a great company, and one of the major businesses was utilities. And one data point of utilities, some guy driving a truck for 4 hours and climbing a pole and writing something on a paper with frozen hands. So you're not going to get a trillion of data like that. You understand that? So you need to have some input from hopefully physics or engineering on your system, and that's what we're going to talk about. So if you have a few data, but some stuff about physics, so let me talk a little bit about a particular part of physics-based machine learning, which is physics-informed neural networks. There are others, of course. And you know that laws of physics are expressed as differential equations. So how do we express differential equations? We have to express derivatives through neural networks. And of course, you can, because the output for given set of weights is a function of a function of a function. Of course, you know, there's neural networks got so popular because you can differentiate with respect to W's. That's what you take optimal gradients with respect to. And because you know these functions f are known and their derivatives are known, you can do it analytically. You can also differentiate. So if you go all the way out here, you can differentiate with respect to the arguments of x. And so if you have one layer, undergraduate can differentiate, 2 layers, graduate student, 3 layers, professors, and 4 layers, distinguished professors, and so on. So some people say I got this backwards, but so yeah, yes. So, but the important thing to remember is that for each set of weights, there's no approximation. There's no delta x, delta t. This is precise, right? It's machine precision. There's no errors. The errors is in W and the approximation, right? So that's something to remember. And the physics-informed neural networks, they're done in such a way that, let's say you consider some area. Let's say you want to solve some equation. This is Berger's equation, right? An x and t. And you have some boundary conditions and you want to solve it in some domain. So you want to find a function of x and t that describes the solution. So there are some initial conditions for this problem and some boundary conditions. So either derivatives or values, function equals something, and here say value equal to something. So, and then you put, here, that's where you know the function. That's the boundary condition, the red dots. And the stars are where you don't know the function, but you know the combination of derivatives. This combination of derivatives has to be as close to 0 as possible. So pins is so standard pins goes like this. You take for given neural network, you get and given weights, you calculate the values of derivatives. You put them together in this equation. You square them, and then you calculate the values of function and the boundaries, and so you have a mapping. Your mapping is from x and t to u, and then you minimize, find weights that minimize all this this 3 topics: PDEs and initial conditions and boundary conditions, and you get what's called pins. And the nice thing about it is that if you have initial conditions, so maybe let's go back here. Once you calculate W's, you can evaluate as many points as you want here in the domain. There's no like iteration or anything. You can just you can evaluate, and it's very fast, right? So if you want million points, no problem. Usually the number of points is quite modest inside the domain. So that's why they're being really popular. So you can use some data to determine some parameters, for example. And NVIDIA has been pushing their weather forecasting system called FourCastNet with the FOUR. You can look it up, and there's others comparable models that are based on pins, and that's because you can you don't need to iterate anything. You know, we can discuss how accurate their weather forecaster is, but I'll mention, and this is well known, that the minimization landscape is very complex. You have several things, and that you have to balance, and it doesn't necessarily converge to what you want. If you have multiple solutions, I mean, it's an iterative method, so it doesn't understand anything about stability and instability. It's perfectly happy to find bits and pieces of stable and unstable solution together and merge them. And I can give you explicit examples. For example, Lorentz attractor is one of those things. It cannot solve Lorentz attractor. What we're going to focus on is Hamiltonian system. You have a loss of accuracy for long-term dynamics. I mean, any system, any Hamiltonian system, if you try to simulate using, say, Runge-Kutta, a planet falling on a planet going around the sun, Kepler's problem, you'll see planet falls very slowly on the sun, or not so slowly, depending what your accuracy is. So to address that, there's people derive structure preserving algorithms and variational integrators. Interesting thing in pins, if you just do what I told you to do and try to solve Kepler's problem, it doesn't even do one revolution. It just flies away. So pins is not very good for Hamiltonian system. So here is some background in Hamiltonian systems for those of you who may not be so familiar. And this is a shameless plug. You can read it in any books of Hamiltonian mechanics. You can also read it in my book of Hamiltonian mechanics. So I try to be very short and concise, but it has a little bit of geometry and advanced math, but not too much. So it's a lecture notes basically for my course. So anyways, if you have a system of ODEs, if U dot is f of ut, and if U can be separated in QP with, let's not get too abstract, Q is called coordinate and P is momentum, then if there is a function H, we call it Hamiltonian, such that dH dq equals Q dot is dH dP, P dot is minus dH dq, then it's Hamiltonian system. And if you have any function of P and Q, you take the time derivative of that, and you see it's satisfied this object called Poisson bracket, canonical Poisson bracket, and it's just chain rule here. So that's all really well known. And then if you have a non-canonical systems, there's no P's and Q's. So if you have a phase space Q and you need the phase space Q and existence of Poisson brackets that maps any two functions, scalar functions, into a scalar function. And then in some abstract sense, U dot is UH is the equations of motion. Of course, U is defined only for scalars, so it's component wise. And a Poisson bracket has to satisfy four properties: antisymmetry, bilinearity, Leibniz rule, so it works as a derivative. And the hardest part is Jacobi identity. And this three is easy to cook up anything that satisfies these three things. The fourth one is really difficult. So if somebody gives you Poisson bracket, can verify that it satisfies or doesn't satisfy, but sort of to cook up general thing is you have to solve some equations that you can't solve. So examples are Euler's equation for rigid bodies is Poisson, but not canonical. So there's Poisson bracket like this. As I mentioned, you can cook up the Poisson bracket using du dt is some tensor, and it's called Poisson tensor B of u. And if B is antisymmetric tensor, then you can see the first three equations are satisfied. And for canonical system, it's a symplectic matrix. And you see that it satisfies Jacobi identity. The bracket satisfies Jacobi identity if only if this tensor PDE is satisfied. And it's basically impossible to solve for all practical purposes. And so if the bracket is may be degenerate, so it has Casimir invariance, and the Casimir invariance is functions that Poisson commute, means with any function f. So it means if you put it in and you put any function f, is going to get 0. So C is conserved for any Hamiltonian. There's a special property of the bracket, and we will mostly consider system where B is linear in U and of particular type. So let's go to what I mean by database simulation of Hamiltonian system. And so, as always in machine learning, there's a question what we do in as far as what is allowed to be known, what is not allowed to be known. But here's the problem: you have some phase space, and you have some data in phase space: U0, U1, U2, U3, and so forth. And you want to determine what the system is and what it will do in the future. Now, one method is learning the equations, and there's a big literature in that. Now, if you didn't have, so you know that the system is Hamiltonian of some sort, right? And of course, if you don't have this restriction of Hamiltonian, then there's many ways because you don't have to satisfy some structure or whatever. But the fact that it's Hamiltonian makes it more difficult. And so people wrote a bunch of papers where they satisfy the equations. So they write the equations in such a way. The equations are, they never learn the Hamiltonian itself, but they learn the system as an output of some neural network, and neural network satisfies some equations of some restrictions on being canonical. So this is only for canonical systems. So the first one is called Hamiltonian neural networks, and it was done by Graydon, Zamba, and Yosinski. And the interesting fun fact is, so one of those authors, and I forgot who was in Google, one is in Uber, and third one I forgot, some other company like that. So it's not some kind of abstract nonsense that nobody needs. So but if you do that, if you discover the equation, you still need to solve it by numerical integrator, and usually, something that satisfies something symplectic, and most of the time they're implicit and so on. So you have that restriction. I mean, there's nothing wrong with it. It's just as long as you remember, you have to do another step. The first folks over there, they did actually run the kata, which is a little questionable. So then there is a recent paper about learning Poisson bracket, and I don't quite agree with that, because I think learning Poisson bracket is dangerous. I mean, it's fine paper, but the problem is about learning Poisson bracket, you don't get the exact conservation of this equation, the complicated tensor equation that I wrote won't be exactly satisfied. And in my opinion, the Poisson brackets should be given, because if you get that, this coefficient is 2.98 approximately, plus minus, well, it doesn't satisfy Poisson, it doesn't satisfy Jacobi identity. And if you don't satisfy Jacobi identity, all kinds of things break down. Everything that will going to base our system will break down. So it's a little dangerous. And then there's some work in dissipative system. We're going to talk about it later a little bit. But we are going to talk about learning the mappings directly. So for us, there's nothing in between U0 and U1. There's time difference, and that's it. We're not interested in what happens in between. We're just interested in what happens in the discrete time points. And so we're just going to create the mappings that approximate the equations as much as possible, the phase flow to be precise. And then you don't need the numerical integrators. The solution is very fast. So what we're going to base our discussions on is the database simulations using symplectic maps. And if you have any equation, U dot is F of UT, it generates the mapping in phase space. And if you have a canonical mapping, it satisfies Poincaré theorem. So for canonical system, you have this for any T, this composition of matrices, it gives you a symplectic matrix, this Poincaré's theorem. And for general Poisson system, phi is Poisson, so it preserves Poisson bracket. And the Jacobi identity is very important, because if you take left side minus right side, take ddt of that, you get exactly what's called Jacobi. So if Jacobi identity is not satisfied, this is not true. So then the main idea for canonical system was done by Jin et al. So they created a sequence of symplectic mappings in phase space PQ, and they don't have to come from any real Hamiltonian. They were just something they created, and they mapped. And they said, well, they proved the theorem that this mappings, the composition of this mapping is dense in space of transformations. And then you need so many of them to approximate any symplectic map. And so they got good results. For example, the Kepler's model and so on was pretty good. And then I don't have time to talk about it, but another alternative is database canonical transformations, which is pretty interesting. So you have to solve Hamilton-Jacobi equations and things like that. Now, then they decided to go next to the Darboux-Lie, to the non-canonical system, and then they used the Darboux-Lie theorem, which says that, well, let's say you have a n-dimensional Poisson system with d Casimir's, then n minus d is even, and there's on the symplectic leaf, on the surface, Casimir is constant. There is a canonical system of coordinates. And what they did is they said, okay, so you have a system here, and they map it and define the transformation using sort of an encoder-decoder, so the forward and backward mapping. And then they used their sympnets on the symplectic leaf, and they mapped it backwards. And it worked for the examples they said, but there's a problem, and I tell you this is a very severe problem with their method. There is another paper which by Bayars, and he did a couple of problems, and he designed this transformation, but he said, I don't know why they work. So, I don't have any completeness or anything like that. And Lacquero et al. Is interesting. They put their paper, I believe it's published now, probably or in press or something like that. I know one of the co-authors, David Martin de Diego, and they put their paper on arXiv one day after us. So I wrote to David Martin, and so they were basically solving the similar problem, but their method is based on solving Hamilton-Jacobi equations, and it's not always possible. So they had some examples where they could, but it's not always easy to do. Because, well, solving Hamilton-Jacobi equation is tricky. So the problem with using the Darboux-Lie theorem is that it is actually not a good theorem for numerical analysis. In fact, some very well-known folks who do calculations of symplectic of Poisson systems, they say this is stay away from using Darboux-Lie theorem. It's not a practical theorem. It's and the biggest problem with the practicality is this word local. And the Darboux-Lie transformations are only guaranteed to be local. They're not guaranteed to be global. So the example is what I wrote here in SO3 equations that we will study. We'll give examples, sort of like a satellite rotation or something like that. The symplectic leaves are spheres, and so there's no global mapping from plane into sphere. Everything they had in the paper of Jin et al. Had the global transformation, but they don't exist by definition. So they made up examples where transformation was global. And then, of course, if the transformation is not global, then these encoder and decoder have to satisfy the sort of mappings of the manifolds and have to intersect, and it's not clear how it works. And of course, also then they don't have the and they don't have the accuracy. I mean, the accuracy is limited by these transformations and so forth. So we will talk about Lie-Poisson systems. And here's a sort of crash course introduction to Lie-Poisson systems. So of course, everything is canonical. Then you have, but let's say you have configuration manifold that's a Lie group. So this is the simplest version. And you have cotangent bundle where you have the point G and P is the momentum. So you have the canonical bracket, but it's complicated bracket. It's some kind of matrices, and it's ugly to use. Now, if it happens, I mean, it's not always guaranteed, but if it happens that the system is invariant with respect to the same group, G, then you can cook up a variable which is either G minus 1P or PG minus 1, and it's called reduction principle. And you know that your Hamiltonian will depend on this variable mu. Which one to take, it depends on physics, but one of those, left or right invariant. So the stuff we'll talk about is mostly left invariant. Then it's guaranteed that if you make this bracket, which is just the Lie bracket, so dft mu is in the Lie, the dual to Lie algebra, so dft mu is in Lie algebra, so dft mu dg d mu, it's a Lie algebra bracket. You can do the pairing with mu and get minus plus, depending on if you have left or right, and that's your Lie-Poisson bracket. And the only thing you need to do is to prove that it's a Poisson map, so it preserves Poisson bracket. And so the fundamental approach is as follows. You have, so that's why we believe that if you know the system, you're allowed to know what kind of system you're solving, right? Is it like a satellite or, what wave or whatever, right? So then you know the symmetry. And so if you're spiritual, you think that the symmetry comes from higher being, right? And so the Poisson bracket comes from the same source. And so the Casimirs should be conserved because they're property of the bracket. But Hamiltonian is basically done by humans. It's it's the where the engineers put the bolts on the satellite and then like a certain Hamiltonian. So if you have the choice between the Casimir and Hamiltonian, you should conserve Casimirs. It's clear, right? So this is what we're going to do. We try our best to conserve Casimirs, and we will be successful in that. And here is some examples of Lie-Poisson systems, and I played some role in some of those papers, but there are many examples of Lie-Poisson system precisely because of symmetry of physical system. And here's some applications that we're doing right now of, for example, you can do the onboard computing on satellites, which requires very light computation because the computers used on satellites is roughly equivalent to Raspberry Pi, so you're not going to compute anything heavy on those. Or with Sandia, this climate group, they're interested in speeding up their computations of really small boxes for their climate models. And so we kind of hope that this will improve our computational power for those. So here's how we define the LPNets. So the nice thing about it is, I mentioned it again, if you take any Hamiltonian, doesn't matter which one, as long as it's not constant, it generates some flow, and the flow is completely legitimate. So if you take a Lagrangian side, for example, you take a Q dot, Lagrangian is Q dot minus Q. You put it on the Lagrange equation, you get 1 equals 0. Right? So, but with Hamiltonian, there's no problem like that. You can take any Hamiltonian you want. And you take a Hamiltonian simple enough that you can solve the the mapping, the forward mapping, so you can integrate Hamilton's equation. And which is kind of fun because it's really fun to solve equations exactly, right? And then you get the motions, the mappings in phase space that are Poisson. And of course, these mappings are defined for your Lie bracket, for your Lie-Poisson bracket, so they will preserve Casimir's to machine precision. And then you build your network out of these maps, right? So, because it's I mean, we're going to talk about small steps, right? And then you have a local. Locally, you can go and we're talking about simple group, compact Lie groups and so on. So locally, you can go to any place on Lie groups, and it's much easier to deal with. So there's all transformations that are really easy to work. We are trying to do the applications to infinite dimensional system, but there is issues with discretizations. And then you get into all kinds of issues with completeness. And I mean, working with infinite dimensional Lie groups is not something I love to do, to be honest. So let's go back to parameterization of how we parameterize Poisson transformations. And so the flows, we do the linear Hamiltonians. I say, remember I said it doesn't matter what Hamiltonian you take, as long as it's not constant, you can generate the flows. And you have a coordinate-free version is, mu dot is minus z star, but it's some linear equation, some matrix depending on A. And the solution is just a matrix exponent, right? And so you can write it explicitly in terms of sines, cosines, exponent, t's, and so on. And so what you do is you do a few steps and sub-steps, and you need a few steps, at least as many as is dimension of your group, but hopefully maybe a little more, depending on the version you say. But it doesn't matter that it deviates in the middle, right? So you have the 3 sub-steps using those transformations, and you map it, you want to map it to the end, right? So the beginning and end should match. But whatever happens in the middle doesn't matter. So here's an example, the rotation group, SO3. Here's a bracket that I wrote. And physical Hamiltonian is a quadratic Hamiltonian, where I is tensor of inertia. And for our Hamiltonian is just a constant rotation. So the true Hamiltonian is some elliptic function that Euler figured out. Our Hamiltonian is just rotation, but a nice thing about it, you can go from any spot to any spot on a sphere, on a momentum sphere. And of course, you preserve the Casimir, which is the absolute value of momentum to machine precision, because all the terms preserve Casimirs. So you built out your system out of rotations, and it's clear you can get from any point to any point in the sphere. So they will consider 2 types of LPNets. One is test Hamiltonians are linear, and then we can so sometimes like for SO3 group, you can find beginning and end, and you can find A's exactly, but most of the time you cannot find A's exactly. And then we do what we call global LPNets, which is the test Hamiltonians are arbitrary functions of those, and I'll talk about those later. And then once you learn the mappings, you can just iterate forward very quickly using either one or another. So those of you who know my musical taste know that I'm a fan of Elvis, and there's several things we can learn from his legacy applicable to this problem. And so there's some basic information about our algorithm, but the important thing is here is for doing The ground truth is we use the backward differentiation formula algorithm with high accuracy. So we have the results were ground truth consistent for all our results. And so time step would be 0.1 for all simulations. And so here's an example of a Kirchhoff equation for underwater vehicle. There's a linear and angular momentum. So angular momentum is pi and linear momentum is p. And there's the bracket is the SE3 bracket, the group of rotation and translation, and sort of looks like this. So well-known stuff. And most of the time it's non-integrable. I mean, it's the same deal as heavy top. So actually the same bracket as heavy top. And there are two Casimirs, p squared and p times pi. And there's two test Hamiltonians you could do. And you can see that it fits the theoretical and practical curves. Theoretical curves are really well. So blue is exact and red is ours. And you can see there's a little discrepancy, but the real discrepancy is because this is chaotic system, and you cannot have a better, faster growing, slower growing error than the e to the lambda t, where lambda is the Lyapunov exponent. So our growth of errors satisfies the Lyapunov exponent. So, but for GLPNets, I will mention briefly that you go into a generalization of this Hamiltonian. So instead of AK mu, so to have sequence of Hamiltonians, you get arbitrary function of that. But this, because Hamiltonian is constant on every time step, the argument is also constant. So what you get is basically a prefactor, but the prefactor depends. So you can still integrate it out exactly, but the prefactor depends on where you are. So the motion is different. And then the difference with the GLPNets is you have very low dimensional or very low dimensional network, just a few parameters, but you sort of try to squeeze all the data at the same time. So, for example, for rotations, for SO3, we do rotations around the basis axis, 1, 2, 3, 1, 2, 3, 6 rotations. And each rotation has 3 parameters of rotations. So, and we are the first ones who did the whole space learning of SO3. So only 1,000 trajectories and initial conditions from a cube. And, it converges pretty well. And you can see, so you can see that our Hamiltonian is, of course, conserved worse than the ground truth, but the Casimir conserved better because the ground truth is doesn't know anything about Casimirs. It does what it does. So it actually, no matter what the accuracy of your data is, it will conserve the Casimirs with machine precision. Of course, every component will lose accuracy if you have worse data. But the combination, namely the square of each square of all components, will be preserved to machine precision, right? And so you can see that this is I only presented 5,000 time steps, so t equals 500 because it just doesn't fit. But this is all 10,000 time steps, and you can see that you don't see the difference. And the difference in the error is just because of time mismatch, but it follows the same trajectory, basically, for a very long time. And so this is the first time we did so anybody did the 3D, as far as I know, 3D learning of SO3 in the whole phase space, right? So it's not just on one Casimir surface or something, it's a whole phase space. And these are randomly chosen trajectories. So let's go a little bit further and go to coupled Lie groups. So I remember I told you about the position about the PDEs, right? So how do we discretize PDEs? And we spend a lot of time thinking about things like shallow water theory. And as it turns out, the Eulerian system, and I have to be honest with you, the Eulerian systems are a little bit difficult. And that's because these LPNets at some point run into the question of interpolation. There's no interpolation that is there's no interpolation that is structure preserving. This I don't know. So if you know structure preserving interpolation, let me know. But for Lagrangian approach, you can do it, and so this is the next thing we did. So the Lagrangian approach is usually used for continuum mechanics, elasticity theory. So this is an example of elastic rod. And it consists of several elements, which are, so if you discretize elastic rod, it consists of elements of SE3 group. So this will be Coursera rod. And each element, of course, if when you symmetry reduce, each element is becomes an element of in the Lie algebra, or Lie algebra star. But there's also relative orientation and position, how you twist neighboring elements. And so it doesn't just reduce to Lie algebras or dual to Lie algebras. So you have this elements of Lie groups. And for example, for two elements, I'll write this. This is we wrote a paper a little while ago about it. And the P is mu is an element of a momenta, so element of dual to Lie algebra. And P is an element of Lie group, right? So this is an SE3. But I mean, this is a coordinate free, but if you write it out in terms of SE3, you get a bunch of equations there. It's in our paper. And you get some ugly looking Poisson bracket. It's not, technically speaking, Lie-Poisson or anything like that. So, yeah. But as it turns out, you can cook up the sort of LPNet-like things. So before you had these Hamiltonians, but now you can have Hamiltonians depending on just the group element. And as it turns out, that's enough to map, to find all the motions. And there, of course, every motion is going to be sort of Poisson in terms of that Poisson bracket. And it's sort of a minor miracle that this Hamiltonian integrates out, right? Because it's like a really complicated looking equations and so on. But if you put it in, then you can find analytical solutions. And we call them LPNets, CLPNets, couple LPNets, and you basically make the transformation obtained from this and transformation obtained from this, and you just put them in some combination, and you get the result. And so here's the result. The two connected elastic elements. So this is SE3 algebra, and SE3 group. So 6 plus 6 plus 6, 18. And the nice thing about it, you can see it's pretty good. You have, you only needed 1,000 data points to do this. And remember I told you, so this is the whole space learning, the whole 18-dimensional space. And when I did the simulation for the previous SO3 group, it's 3-dimensional. So I thought 10 to the 3, you cover the whole space. So I thought, well, this is 18-dimensional, so 10 to the 18. No, this is like my laptop will die, right? And any computer will die with 10 to 18 data points. But it's still the same 1,000 data points. I mean, it's not as good as the other one, but because it's a really highly chaotic system, so you can't expect it to be good. So if you put more data, you will get better results, but you can also see the Lyapunov exponent fits and so on. So, I mean, it's kind of impressive, and it's very light, only 189 parameters to describe this really complex system. And you can see that, so that the error goes the right way. The energy is more or less conserved, and two of our Casimirs are conserved with machine precision. There's two Casimirs. I found these two Casimirs I was very proud, and then it turns out that Jerry Marsden and collaborators found it 25 years before me. So, but it's it's okay to lose to Jerry Marsden by 25 years, I think. And so just the last step, I wanted to talk about dissipative system. Now we enter the dark forest of things not known. So there's no symplectic information anymore. So you have, well, I wrote canonical dissipative system. So you have P dot, this is the force, and force is dissipative. So you have something called entropy, and the second law of thermodynamics says that the law of entropy, TdS, has to be larger or equal than 0. And how does it, what can you say about the mapping from initial to final states? Nothing, there's no Poincaré theorem, nothing at all. The only thing we know is that friction force has to satisfy this for all the Q dots, all the motions. So, but it's larger or equal, not equal. So, but we could do something. I mean, there's many ways to learn equations that without structure, but here is sort of a structure, and the structure is that it's dissipative. So metriplectic is one of the popular ways to describe this, and people did some interesting equation discovery in metriplectic system. So we did a little bit alternative. So we used the variational theory of Hamiltonian system with friction. Well, I mean, technically speaking, so Francois and Hirako Yoshimura had a series of interesting papers about that, and they did it on a Lagrangian side, but you can do it on Hamiltonian side as well. And so the idea is, because we're talking about Hamiltonian side, you have a continuous action principle and subject to two constraints. One is a constraints of variation, sort of Lagrange d'Alembert, and one is the thermodynamics constraint. So it's an old familiar variational principle, but with constraints. So that gives thermodynamical correct system, and you discretize it. And we're writing a paper right now about you discretize it by putting the differences, the dots into sort of discrete differences, and this is just a simple one, right? The first order. You can do higher order and so on. So and you can discretize H in high order. So you can write the discrete variation principles the way you want, but then you will have to be consistent and take the variations and get some complicated looking variational principles. So in previous works, Francois and Hiro had some examples for various system. We had to tune it up a little bit for our system, but basically you have an implicit scheme that connects the beginning and end of every trajectory. And so for numerical solution is difficult because you need to solve some implicit equations, which is difficult. But it's wonderful for machine learning because you actually have beginning and end. I mean, this is what's given, right? At every time t and t plus h, the data is given. So you actually just substitute this into phi and find all the mappings you want. So this is as close as you can get to sort of structure preserving machine learning for dissipative systems. And so we there is a little bit more in this paper, which I don't have time to talk to, and it's this you have to make sure that that the force is strictly dissipative. So in all your machine learning mappings, whatever your approximation for the force is, it has to satisfy second law of thermodynamics, right? That's a very essential part of this. And you can see that this is a problem of adiabatic piston. It's a very interesting problem because it's considered an elementary problem. It's in Landau and Lifshitz. Then people disagreed with Landau and Lifshitz, and there was, even though everybody says it's a textbook problem. So if you have two containers and they have temperature and X, and they're connected with a piston that goes back and forth, and it's completely adiabatically isolated. So if it's not adiabatically isolated, the temperatures will be equilibrated. But there's quite some contradiction in literature. I invite you to read this nice paper by Gruber about the solution. And so it's very easy to get this problem wrong. And I agree with his statements, what the final equilibrium is. And you can see that our result finds the equilibrium consistent with what Gruber said. So anyway, this is all I have. As far as the next step, we do optimal control of systems on Lie groups. So if you have drones that are flying, for example, and collaborate, there was a paper on by Just and Krishna Prasad, a very nice series of papers. Not just that, but this is one example. And as it turns out, they're reduced to Lie-Poisson system, but the Hamiltonian is not, physical Hamiltonian. It's a contracted Hamiltonian, comes from optimal control, and then there's symmetry reduction. And another one is something that's we had a chance to discuss during dinner, the neuromorphic computing and spiking neural networks. The thing about spiking neural networks, they suggested as one way of solving the AI's thirst for energy. They're very energy efficient. They sort of work on the principles how our neurons work. But of course, because they're spiking, they're temporally and spatially discontinuous, so you can't really do the gradient descent, or you can't put derivatives of functions in it, and so it's very difficult to solve differential equations using neuromorphic computing. But in our case, we integrated the equations out, and so while we cannot train our networks on on spiking networks, we can at least program spiking networks to do those mappings. So that's possible. So, and then also another shameless plug. So I teach online course at the University of Alberta. It's very hands-on, 3 times a week for 3 weeks, 4 hours, just standard pins, but very, very hands-on, and using Google Colab all online. And so we charge a little bit of money, but it's not, very modest amounts. And so if you have students or postdoc who are interested in that stuff, I'm not going to talk about any of these things, but we do the sort of the good and bad and the ugly of pins. We talk about some industry-related problems, and they will have their own pins related notebooks they can play with. And so if you know students or postdoc who are interested, please let them know. We're probably going to run another course in the summer, and we're going to start registering somewhere April or May soon. So anyway, thank you very much. That's all I had.
Questions or online?
Do you want to have a look online? I don't know how to. Like you have to.
It should pop up. I think. Oh, there's something.
Okay, something.
That's just Nathaniel, right?
Oh, okay.
Okay, no.
Okay.
Okay. Any questions?
Yeah.
So, thanks for the amazing talk. I'm very impressed by the emergent results. And, my question is, for your algorithm, was the conservation of Casimir was the most important part, or which one would you identify the most important part so that you get the good results?
Well, I think it's conservation of Casimir's, but also the energy shouldn't sort of go crazy, right? So the energy should be just like in most variational integrators. The energy should be more or less conserved, right? I mean, there's no way to conserve them both, but the energy should sort of wobble around or don't do anything bad. So if you have a lower enough dimensional system, then this two is not, is enough because it restricts the phase flow. So SO3 is of course special because Casimir makes a sphere and energy ellipsoid intersects that sphere, and then you're only allowed to move on that closed curve, right? And then there's nowhere to go, right? But more high dimensional systems, I mean, it restricts your Casimirs restrict your motion. Energy also restricts your motion. But if you have a high dimensional system, I mean, you still you can have a chaotic dynamics on these surfaces, and that's what happened with, for example, the joints I showed. I mean, it's a very high dimensional system. There's two Casimirs and one energy, but it's 15-dimensional system, chaotic system, so it still runs away from you. But at least on 15-dimensional surface rather than 18-dimensional surface.
You notice any difference between integrable and non-integrable systems?
Yeah, integrable systems work way better. So yeah,
So you see that in
yeah, so because whenever you have Lyapunov's exponent, you have this growth of error, exponential growth of error, and you can press it. And I'm actually thinking about doing that. So Ed Ott has some really nice work about how to drastically decrease that prefactor in the chaotic system. But if you have an integrable system, I mean that is zero. So yeah, the integrable systems they produce really nice pictures for complications. So yeah, but the integrable systems are much better.
You said early on, right? So you're learning the flow, sort of like the mapping from UN to UN plus one. After you learn that, can you go back and then learn the equations, motion, or?
I guess in principle we could, although it's a little hard to extract it from our stuff because it's just I think you can probably make use like I don't know, GPONet or something like that, but yeah, I think in principle you could learn the equations themselves, and then the question is like, what are you allowed to know about equations? But I think if you're allowed to know the Poisson bracket, you could probably learn the Hamiltonian as neural network, just by sort of doing experiments with your map.
Any other questions? Like when you learn the flow, it's like it depends on the time step.
It does
Choose
depend
for
on
your
time
data,
step,
right?
yes, yeah.
And can you like extrapolate the different time steps?
Yes,
Yeah.
yes. It's just it's a little bit annoying, but yes, you can extrapolate, especially in this variational dissipative stuff. Then it's pretty straightforward because time step is explicitly a function there. But yeah, you can do it as a function of time step. It's just a little
Okay, so
work.
it's like you put the time step in the neural net or something.
Yeah, you
And
put
then train with different time
yes,
steps.
yeah, but you need data with this. Yeah, we didn't do it.
I would guess some data comes to you with like very time steps, like it's not always uniformly spaced or something.
I mean, there's also
Real applications or something.
Oh, and the real application, I don't know, it's, I mean, when I work with the Air Force guys and they actually have a problem on